Today we will be learning about recirculation boundary conditions. Let's start by building a simple model. I'm going to start by adding a static body tank. And I'm going to choose a flat bottom and eliminate the baffles. I'm now going to add additional geometries to this static body family. I'm going to add a cylinder and move it off center slightly. Now I can use this cylinder for boundary conditions. I can define my boundary conditions inside of the inlet and outlet option under geometry. You can have moving inlets and outlets, but usually you're going to be using static ones. I have three options for defining the inlets and outlets. I can use the point on bounding box, which lets me choose a point on this kind of orange model, and I can center it over the cylinder. This would represent inflow over the entire tank area. I can also use surfaces, which will allow me to define an entire face of the geometry. So I can choose this entire bottom of the cylinder or any other surface that I decide. Often the easiest way to define a boundary condition is with edges. Edges are easy to use because it allows you to select geometries through walls or inside of other geometries. So here I can choose either end of the cylinder I placed inside of the tank. You do have to make sure that behind the boundary condition there is no fluid but a static solid object. Otherwise the boundary condition would be confused and not know which was the in and out and how to function properly, because a boundary condition cannot be floating in space. As the name suggests, a boundary condition needs to be defined on a boundary. However, in this instance, the cylinder can be open or closed. And so I could make the top open or the bottom closed or any other arrangement. So now that the top is open and the bottom is closed, I could create a boundary condition on the bottom of the cylinder pointing up. Let's see if that works when we run it. It looks like the code is giving us an error. It says that there are multiple fluid cells next to a boundary condition. This is because we created a boundary condition without anything solid behind it, and so the code doesn't quite know how to teleport in the fluid and make it work properly. To fix this problem, we need to close this region. So let's add another cylinder and put it just below the one we already have. We need to give it a top. Now this is going to run properly. Now that it's running, we can see that the code is working just fine. This is one of the most common sources of errors when working with boundary conditions. Now let's add a second boundary condition. I'm going to use a really nice feature. If you select your cylindrical tank walls and then click More, I can add a pipe directly to the model. Now that I've added this pipe, I'm going to increase the diameter a little bit. Notice also that this automatically generates a boundary condition. You can delete that if you don't need it or want it, but I'm going to move this pipe around a little bit like you can with other geometries. I like where it's positioned now. and it has the boundary condition in the pink arrow. I can also set it to be flush with the walls of the tank, which is a little more realistic. I'm going to rename my boundary conditions so they're a little easier to use. So I right click and click rename. I'm going to make this one my inlet. When it comes to choosing the boundary condition type, I have a lot of options. I can do pressure, velocity. Outflow is really useful as kind of an outlet option. I'm going to show you a little more about recirculation later in the video. You can do poisson. There are also options to do volume flow rate, mass flow rate, and impulses. These bottom ones are basically velocity, but sometimes it's more convenient to use these options. For right now, I'm going to stick with velocity and use the default 1 meter per second. Let's take a look at the other boundary condition. Let's right click on it and rename it outlet. We could use outflow or pressure as a boundary condition for this outlet. And to make it a little more exciting, let's add a free surface. And I've set this free surface so that when it comes through the inlet, it's going to hit it right away. There's a couple other settings we should tweak. I'm going to give it a little bit of a ramp for the inlet. I will reduce the simulation time to just 20 seconds, and I'm going to increase the resolution to 150. That resolution gives me about 10 lattice points across the inlet, which is plenty for what I'm doing. Something to keep in mind is that boundary conditions sometimes require a smaller time step. Just to be safe, I'm going to use a time step that's half as long as the default value. And everything else looks good. So that is how you set up inlet and outlet boundary conditions. The last thing I'm going to do is add some particles. The software automatically prompts me to choose a geometry, but I can actually just skip this step. And under the injection dropdown, I can choose boundary conditions. So I can use my inlet as the injection point. And I'm going to go ahead and dump, let's make it 100,000 particles at 2 seconds into the system at that inlet boundary condition. Now let's run it and see what this looks like in post. I've sped up the time a little bit. This took about 20 minutes total. Here is our model. We can see the fluid coming in through the inlet, as well as the particles in the free surface. Let's recolor the fluid by Y coordinate. Great, let's start it over and press play. There we can see the impulse of the particles at 2 seconds. We can look at some of our data tables, and here's the flow rate, for example. And looking at the flow rate, we can see after about a second of ramp time, it's up to speed. Here's the outlet data with the flow rate. As you can see here, the pressure is remaining constant and the flow rate is decreasing over time. Let's take a look at the fluid data. It looks like The fluid volume is decreasing, so the outlet is pumping out more than the inlet is pumping in. It looks like I could reduce the LB density fluctuations a bit. So for next time, I will probably reduce the time step a little bit. Let's go back to the rendering, and why don't we take a look at the particles. All right, here we see the initial impulse of particles at 2 seconds, and we can see how the number of particles decreases over time as they are slowly pumped out of the model. This kind of graph might be useful if you wanted to calculate a dilution rate or some other metric to evaluate the performance of your system. Let's take a look at the outlet. I'm going to turn off the particles so it's easier to see. And we can see how the outlets create a small vortex as it draws the fluid into it. I'm going to press play from the beginning again, and we can see the fluid coming into the system. And I suspect that if we let the simulation run longer, we would see the free surface drop until it reached the outlet. There's another really interesting way to visualize this data, and to do that, I'm going to switch to 3D volumes. I'm going to turn off the particles again. And I'm going to change the colors a little bit and turn on shade just to make it a little easier to see. What I'm going to do is go to filters and add stream tracers or streamlines. I'm going to originate them with a point cloud. What I want to do is center these streamlines in the inlet pipe. And to do that, I'm going to move the sphere to the pipe. Now I'm going to put in those coordinates. And it looks like it is just a little bit off still. I need to up the X value a little bit. And there it is. Now it's centered right on the inlet pipe. Lastly, I'm going to make the point cloud a little smaller so that it fits inside of the pipe. I'm also going to set these streamlines to move forward, not in both directions. So let's give them a solid color, so now we can start to see them inside of the render. I can also change the number of points, and perhaps more interestingly, I can change the length of those points. So now we can really see how this fluid is moving throughout the model. Oh, we can start to see the fluid wrapping around the model, and let's make them even longer. And we can really start to see the circular motion and even some of the structures inside of the fluid. I can also render them as tubes by increasing the thickness of these streamlines. And this is just nice. It gives you a little bit more contrast and depth perception. That was a fairly basic example of using boundary conditions. Now let's look at a more advanced example. Let's look at recirculation. With recirculation, it couples together an inlet and an outlet. So the fluid leaving through the outlet will re-enter through the inlet. I do have the ability to control or limit how much of that fluid is recirculated. But let's go ahead and talk about how to create that inside of the system. So first thing I'm going to do is pretend that the outlet has some kind of pump. And so I'm going to use velocity and use a constant velocity. And I'm going to flip the direction. And let's keep the velocity magnitude of 1. Now there's going to be a constant outflow down. Now I'm going to change the boundary condition for the inlet to recirculation inlet and then link it to the outlet. Now I can also add a delay to the recirculation, which is, what we would expect in most real-world applications. So why don't I add 3 seconds so that there'll be a 3-second delay between when the fluid enters or leaves and then enters the system. I can also add a flow rate ratio. So I can say 0.8, which would mean 80% of the fluid re-enters the system and 20% does not. This won't influence any of the physics involved, but I'm going to add a scalar field. And I'm going to skip adding a geometry again. We're going to set the outlet to 0 gradient and then the inlet to recirculation. That will keep the same variables we set before, like the delay and flow rate. C stands for complete, meaning the entirety of the mass of the tracer that leaves the system will re-enter the system. Let's just write a small UDF that will create a pulse of density that enters the system. So if time is less than 5 and less than 5.1, the value will be 10. Else return C. This UDF prescribes that after 5 seconds of fluid motion, we will pulse the system with a scalar concentration of 10 moles per liter at the inlet. Following this injection, the inlet simply recirculates what is leaving the outlet. And that's pretty much how you set up a recirculation. Let's go ahead and run it and take a look at it in post. I'm going to start by coloring the free surface according to the magnitude of the y-axis. Let's hit refresh and press play to watch it. There we have the particles entering the system after 2 seconds. And now we're starting to see these particles re-enter the system. So after 2 seconds, the particles entered the system, and then a couple seconds later, the particles leaving through the outlet are returning again through the inlet. Let's take a look at the scalar. So we're going to load 3D volumes now. So to see the scalar a little better, I'm going to color the volume by scalar concentration. And let's tweak the colors a little bit just so it's a little easier to see. And let's restart and watch again. So there comes the scalar as it enters, and then it gets recycled again. Note that the concentration seems high on the inlet, and that's because we set the flow rate ratio to be 0.8. So 80% of the liquid is re-entering the system. However, 100% of the added species will be remaining in the system. There's a higher concentration of tracers per volume. So in the real world, you could imagine some kind of buffer or mechanism that concentrates the solution and returns it back into the system. That's about it for recirculation in tanks. Thank you so much for watching. Please don't hesitate to reach out if you have any questions.